everyone, and welcome to the third week of this course. We appreciate everyone that's been joining from the very first week, and we welcome you warmly to the third week of the course. So, over the course of the first 2 weeks, we've discussed what remote sensing is, we've discussed the form of remote sensing, we've discussed the process of remote sensing and the applications of remote sensing. So, basically, that was what we did the first week. So I'll link the descriptions to the videos we've done in the past in the box in the description in the description box, so you could just um, go through week one. And for week two, we that was last week, we discussed the electromagnetic energy, we discussed the electromagnetic spectrum, we discussed how the radiation from the sun, which is the EME, interacts with the atmosphere, and also how it interacts with the target, which is the Earth's surface. We talked about scattering, talked about absorption, and all of that. So I'll just again link the video in the description. So once again, I welcome you warmly to week three. So we would appreciate it if you subscribe to our YouTube channel if your first time if this is the first time you'll be joining us. We'd appreciate it if you subscribe to our YouTube channel. And also we are building a geospatial community, so if you'd like to join our community, I would also drop the link in the description box, the link to our Slack channel where you could join our community. Kindly do well to subscribe and like our videos, and also leave a comment if you find this video helpful. Alright, so for week three, we'll be talking about the types of remote sensing that is the active and passive. We'll be talking about satellites and sensors. We'll be talking about satellite characteristics. Talking about 4 different types of resolution. Then we'll be talking about scanning, and we'll also be showing some video demonstration to help us understand better. All right, so we just get started with passive and active remote sensing. So in remote sensing, like we've been discussing from the beginning of the course, that the main source of energy is the sun, which is used for illumination. But then we tend to but then there's the question, what happens at night when there's no sunlight? How do we continue the process of remote sensing when there's no sunlight? So that is where active remote sensing comes in. So previously in week one and week two, we've been introduced to passive remote sensing. It's passive in the sense that it does not produce its own source of energy. The form of the type of remote sensing basically relies on the illumination coming from the sun. But now, what happens at night, like we mentioned earlier? So this is where active remote sensing comes in. So active remote sensing just it operates during the day, during the night. It doesn't really have any restriction, because it basically produces its own source of illumination. So satellite basically have imaging sensors that are used to monitor the Earth. So this imaging sensor will form the types of remote sensing we have. So we have the passive sensors and we have the active sensors. So the passive sensors are are the sensors that are operational in the for passive remote sensing, and similarly for active remote sensing, we have the active sensors in them. So we just talk about active remote sensing and passive remote sensing. So for passive remote sensing, like we've mentioned earlier, the sun is the ultimate source of illumination. So the sun basically illuminates the Earth's surface, which is the target, and the target reflects the electromagnetic sensor, which is what the sensor picks up. So we've discussed this previously in week one and week two. So this is what the sensor picks up. So basically, this is the concept of passive remote sensing. Without the sun, it can't without the sun sending radiation to the Earth, there's nothing that will be reflected back for the sensor to pick up. So passive remote sensing is only functional when the sun when we have the sun. So it basically operates during the daytime, like at it can't the operation is limited at night, so we can't use passive remote sensing at night. And also, one of the setbacks for passive remote sensing is that it is basically disturbed by weather. Last week we are talking about the interaction with of passive remote sensing in atmosphere, and we mentioned scattering, where we're talking about Rayleigh scattering, Mike scattering, and non-selective scattering. So basically, for passive remote sensing, it is significantly affected by weather conditions like heavy rain, cloud. That's why when we look through remote sensing images, we see some of our images are like basically filled with a lot of clouds. So this is like some of like the setback of of passive remote sensing, because when we have these heavy clouds, they basically obstruct the sunlight from illuminating the target. So at that moment, the target will not be able to like reflect back to the sensor. Basically, what is being scattered in the atmosphere is what the sensor will be reading at that point. So therefore, we have like cloudy images. So that's just a wrap on passive remote sensing. So now we'll move to active remote sensing. So for active remote sensing, basically what it does is that it produces its own source of energy, right? Which illuminates the earth. Like it produces its own source of electromagnetic energy that illuminates the earth, which is the target, and it records the sensor in the satellite basically record what is sent back, like the reflected radiation from the surface of the earth. So this form of remote sensing, it has this edge over passive remote sensing because the radiation can penetrate to the radiation can penetrate through clouds. So if the day is cloudy, if there's haze or if there's rain, we don't have to be worried because we are using like an active source of energy that can actually penetrate through all of this disturbance. And also, like one very big edge it has is also the fact that it operates like during the day and it also operates during the night. So like it doesn't have that restriction that passive remote sensing like has. So it is not affected by poor weather conditions since it emits its energy directly to the target with no interference by, like, it doesn't care about the weather. So next up, we'll be moving on to satellites and sensors. So basically, for a sensor to collect and record energy, it must be on a stable platform. So if you noticed, I've been trying to be so careful with the word sensor and satellite in week 1 and week 2. So basically, the sensor is a device in a platform. So the platform could be the platform basically varies depending on the altitude of the platform. So we have some platforms that are actually situated on the ground, we have some situated in air, and we have some situated in space. So basically, we have our sensor like residing on a stable platform. So the platform for remote sensing may be situated, like we mentioned earlier, situated on the ground, on an aircraft or balloon, and also spacecraft or satellite. So basically, this is where the term satellite comes in. So we'll be talking more about the um, we'll be talking more about the platform. We'll be talking more about the platforms. So let's just dive in. So the first platform we have is on ground. Um, the ground based platform are used to record detailed information about the surface. In some cases, it can be used to better characterize the target. So the sensors are placed. The sensors for the ground based can be placed probably on a ladder, on a scaffold, or a tall building. Basically, so far the platform has contact with the surface of the earth, so we can categorize it as a ground based platform. So next up we have area platforms. So for area platform, basically these are like when we have like drone, we have choppers, we have airplanes. So when we have our sensor in these devices, basically when we have our sensors on this platform, basically, so we categorize that as in air. And finally we have in space. So in space, remote sensing is sometimes conducted from a space shuttle, or what we refer to as satellite. So basically, these are like different satellites. So, but to understand what satellites are basically objects that revolve around another object. So, for example, the way the Earth revolves around the sun, so we can say the Earth is a satellite as well. But in this case, we are more interested in the artificial satellite revolving around the Earth. So we'll just move on to talk about some properties, some characteristics of this satellite. So we'll be discussing a few. We'll just be discussing um, a few. We have the satellite orbit. So basically, a satellite orbit is the part, like we mentioned, this satellite basically revolved around the Earth. So the part that this satellite follows to revolve around the Earth is basically called orbit. Then it's also important to know that these satellite orbits are matched to the capabilities and objective of the sensor they carry. We'll talk a little bit more about them. Then another characteristics we'll be talking about is the SWAT. So basically, the SWAT is okay. So now, if you like draw a line from this point, say from this point to this point, so basically that's the SWAT. So the SWAT is just the width that the sensor can observe. So if you look at this Landsat image, if you look at this Landsat image, you can see the SWAT. So the SWAT is about 185 kilometer. So as the satellite revolves around the Earth, so the sensor sees a certain portion of the Earth's surface. So the area that is the area imaged on the surface is what we refer to as SWAT. That area is seen. That area is seen is what we refer to as SWAT. So this SWAT, they actually vary between 10 to 100 of kilometer. Like their width is always like it varies from like satellite to satellite. So next we'll be talking about the types of satellite orbits. Basically, we'll be we'll be talking about three different type of satellite orbits. So we have the polar orbit, we have the geostationary orbit, and we have the sun synchronous orbit. So basically, the we categorize this orbit relatively to their altitude. You know, the height above um, the Earth's surface, the height at which the satellite is above the Earth's surface. You know, their orientation and the way they rotate relatively to the Earth are basically ways we categorize them into polar, geostationary, and sun synchronous satellites. And sun synchronous satellite orbits. So basically, polar orbits is when the part of the satellite is going from north to south. This orbit, they maintain a altitude of at least 700 kilometer. They are also known as near polar orbits because basically they are like very close. You know, they are very close to the poles. Satellites at very high altitude, which view the same portion of the Earth's surface at all time, have geostationary orbits. So basically, geostationary orbits are satellites with like high altitude. The altitude of geostationary orbit is approximately 36,000 kilometers, and they revolve at speeds which match the rotation of the Earth. So they seem to be stationary. So that's why they get the name geostationary orbits, because the speed at which they revolve is like relatively proportional to the speed at which the Earth revolves. So this permits the satellite to observe and collect information continuously over specific areas. So for geostationary orbit, satellites in the geostationary orbit are basically used for weather and communication because they have a very high altitude. So it is possible for geostationary orbits to cover a large area. Sometimes it can cover about the entire hemisphere of the Earth. So next up, we have the sun synchronous satellite. So a satellite in the sun synchronous orbit would usually be at an altitude between 600 to 800 kilometer. Basically, it has similar properties with the polar orbit. Sun synchronous orbit is a type of polar orbit that travels over the polar region and are synchronous with the sun. So this means they are synchronized to always be at the same position. They are always at a fixed position relative to the sun. So what this means is that the satellite will always visit the same spots at the same time. So for example, say for a local city, say my local city is Lagos in Nigeria. So the satellite will always pass Lagos in Nigeria, say 12 o'clock every day. So basically that's why we call them sun synchronous, because they are synchronized to be in a fixed position relative to the sun. So the fact that these satellites would always observe a point on Earth constantly at the same time of every day, it serves a number of applications. For example, this is very important in monitoring changes over time. So you want to you want to monitor. So basically, you want to monitor how has a particular region change over time. So satellites in this orbit are very useful for that, and also it's also useful to mosaic adjacent images together. As they don't necessarily have to be corrected for different illumination conditions. So a very very useful. This is why the sun synchronous satellites are very very useful. So we're moving on to a short video. So basically, the video is just a demo of how the satellite moves. So it's a 1 minute video. So basically, this is how the satellite moves and covers the entire Earth. So if you notice, it is moving. This is a polar. It is moving in the polar orbit. So it's going from north to south, and the Earth is also rotating beneath it, and it's covering the entire Earth. It's covering the entire Earth. It's covering the entire Earth. And now it's covered the entire Earth. So next up, we'll be talking about resolutions. So we'll be talking basically about 4 types of resolutions. We have the spatial resolution, we have the radiometric resolution, we have the spectral, and we have the temporal. Over time, these resolutions had always been a bone in the neck for people, because I mean people like find it difficult to differentiate between spatial and spectral. Spectral and temporal. What are the differences between this resolution? How do you understand this resolution? So sit back and relax. We'll just try to demystify them in the following slide. So the first is spatial resolution. So looking at this image, we have the image on the far right. It has a high spatial resolution. The image on the far left, it has a low spatial resolution, and the one in between has a medium spatial resolution. So spatial resolution basically is the size of the smallest possible feature that can be detected. Like the size of the smallest possible feature that we can detect. So spatial resolution basically talks about the details of the pixels we have in an image. When an image has an higher spatial resolution, or when a satellite has a higher spatial resolution, it means it would have more details. Like it will show us more details, and the grids are always smaller in size. Like the pixel size are always smaller. Whereas when we have low spatial resolution, it means we have less details. We can detect less details on the image, and the pixel size are larger. So let me use our mobile phones to explain this. So imagine you have a phone, and your phone is 2 megapixel. Right? Say this was back in probably 10 years ago, and your phone was 2 megapixel. If you take that phone and you like take a picture, now the picture are not so clear compared to modern phones we are using today, like with about 64,000, with about 64 megapixel, 12 megapixel, and the likes. So for the 2 megapixel means there are 2 times 10 raised to power 6 pixels in one image. So that means when once you like zoom the image to an extent, you begin to I don't know, it begins, I don't know if you've like experienced it, but once you like you zoom an image like so much, it becomes it get pixelated like this. This is like a clear image, then it becomes, then when you zoom the image, it gets pixelated, you zoom it more, then it gets to a point you would even be able to like pick up a pixel. So now the size of a pixel, like the length of a pixel, pixels are always in grids. That means they are square. So one side of a pixel is telling us about the spatial resolution of that image. So the image you took with 2 megapixel are not so detailed. What you have there are not so detailed compared to the one you took with 64 megapixel. For example, for the 2 megapixel, a pixel might be taken, and this is just like a vague example, not something real, right? So a pixel might be combining your nose and your eye for the 2 megapixel. But when it comes to the 64 megapixel, I mean it becomes smaller, and the details have become refined. So like just maybe 5 pixels are just concentrating on your eyes alone, not to talk of like the entire face. So it makes the picture clearer. It gives you like more sense to like pick. Looking at this now, it gives you it gives you this kind of picture. So this is like what the 64 megapixel looks like, and this is what the 2 megapixel looks like. So next up, we'll be talking about spectral resolution. Basically, spectral resolution describes how much spectral details we have in each band of a multispectral or hyperspectral image. So the higher the spectral resolution, the more narrow the bands are, whereas low spectral resolution has broader bands covering more of the spectrum. Um, for example, a multispectral image breaks light into, by light I mean the electromagnetic energy, into 4 to 36 bands. Then it assigns those bands names such as red, green, blue, and near infrared. So for the image, this is Landsat 8, and we have like the spectral resolution. So for band 1, which is the coastal band, it has the spectral resolution is from about 0.433 to about 0.453 micrometer, and the spatial resolution is 30 meter. For the blue band, for band 2, which is the blue band, this is what the spectral resolution is, from about 0.45 to about 0.51 micrometer, and we have the like. So that is spectral resolution. It just refers to the ability of the sensor to measure specific wavelengths of the electromagnetic spectrum. So next we'll be moving on to radiometric resolution, and I would really like us to like pay all of our attention here, because for radiometric resolution it is a little bit tricky. Radiometric resolution basically describes the ability of a sensor to distinguish between grayscale values while capturing an image. Now, what I just said, what does it mean? So now, if we look at our eyes as humans, we are only able to see the visible spectrum, as we've explained previously. So we're only able to like see like colors in the visible spectrum. So we can say this is blue, this is black, this is white, this is yellow. We can like differentiate between 60 million colors basically. So now, but for a satellite does not see white, blue, black, green, or red. Basically, what satellite perceives are what the satellite perceives are different wavelengths with different intensities. So that is what the satellite sees. Like it sees different wavelengths with different intensity. So what the satellite like sees is just bright and dark, bright, dark, bright, dark with different shades of like brightness and darkness, because it is like sensitive to like different magnitude of the electromagnetic energy, and it is able to discriminate very slight difference in energy. This is what radiometric resolution is. So this image illustrates what I'm trying to talk about. So this radiometric resolution is measured in bits. So the more bits an image has, the more grayscale values that can be measured or stored. That means we can differentiate between different stuff on the image. So for example, if you have a 2-bit image, so basically each bit records an exponent of the power of 2. So if you have 1 bit, it will give us 2. That's 2 raised power 1. If you have 4 bits, it will be 2 raised power 4, and the likes. So for example, now looking at this is 1 bit, right? So this is 2 raised power 1, and 2 raised power 1 is 2. So so this is telling us that it ranges. This is 0 and 1. So basically what the sensor would be seeing is just black and white. Those are just the two intensities. Those are the grayscales you can see, just black and white. But now when it is 4 bits, 2 raised to power 4, that's 16. So it will be ranging from 0 to 15. Now you can see that the intensity level has increased. It can now sense more energy. Before everything from this part to this part was just black. Everything from this part to this part was just white. But now it can sense more. It can distinguish between more grayscales. It can pick more energy level, basically because it has increased to 4 bits. And now if we have 8 bits, I mean, this is ranging from 0 to 255 just for 8 bits. So now look at this, 0 to 255. So you can finally distinguish between different energy levels. So to better understand this, we have an image. So now for this image, we have 2 images, right? So they are showing the same areas. They are showing the same area. So the images are in grayscale. What we have on the left is showing 2 bits, that is 4 shades of gray, and what we have on the right is 8 bits, that is 256 shades of gray. So now looking at this naturally, for 2 bits it has just four gray levels. So it can represent it will represent everything we have here with just 4 shades of gray. So look at the resulting image we have. I mean, I can't even tell there are forests here, but I can't even tell there's a road path. I can't tell there's a road path here. But looking at this, now this has 256 shades to represent the grayscale in this image. So now I can clearly see, okay, this is the forest. Now I can clearly see this is the footpath. So the 8-bit image is showing us more features on the image compared to the 2-bit, right? So now the radiometric resolution is basically the ability for a sensor to distinguish between grayscale values while acquiring images. So I hope we understand that. I just needed to like take my time to explain that, because it's always a problem in remote sensing, radiometric resolution. Sometimes some people confuse it with spectral resolution. So now the last type of resolution we have is temporal resolution. So basically temporal resolution is the time it takes a satellite to revisit a particular area. So say for different satellites, they have different spectral, they have different temporal resolution. For example, for Sentinel, I think Sentinel temporal resolution is 5 to 6 days. For Landsat, Landsat 8 and 7 is 14 days. So basically, and there are some satellites that have like high temporal resolution that like we visit the same spots every other day. So basically that is what we have for temporal resolution. Then finally, we are like moving closer to the end of the course for this week. So we're talking about scanning. So basically, we have two types of scanning we'll be discussing. We have the across track scanning and we have the along track scanning. So for across track scanning, this is an image representing across track scanning. The across track scanning is also known as the whisk probe scanning because of the way it's like images the earth. It images the earth in a form as if you are sweeping, like you are sweeping the floor. You know, if you are imagine you are sweeping the floor, so you are like going like you're sweeping the floor of your room, and you're like yeah going side by side basically. Yeah. I think that makes it better. So it images it images the earth like taking pictures of the earth side by side, you know, taking pictures of the earth side by side. So across track scanner is also known as whisk broom scanning, like I mentioned earlier. It scans the earth in a series of lines, and these lines are oriented perpendicularly to the direction of motion of the sensor's platform. That is why it has the name across the width. An example of satellite that use this system is Landsat. So it is also important to note that each line is scanned from one side of the sensor to the other side. So that's what I was trying to explain about the broom. Like when you're sweeping your room, you're trying to like sweep from one end to the other end of your room. So the next type of scanning we have is the along track scanning. So this is an image that represents the along track scanning. So for along track scanning, it's also known as push broom. It's also known as push broom. This is basically imagine you are like trying to roll a rug. So imagine you're in your room, you have the rug, and you're trying to like roll the rug, like you're trying to roll the rug away. So you're pushing the rug forward, you're rolling it forward. So basically that's how it got the name push broom. It also scans the earth in series of line. An example of satellite that use the push broom is Spot 1. So this type of scanning uses the forward motion. That's why I try to illustrate with the pushing, like rolling your rug. You know, you're like trying to roll it forward. So it uses a forward motion of sensor to detect successive scanned lines, and the lines are all and lines are perpendicular to the flight direction. So that is why it has the name push broom, because we're trying to like push the rug forward. Just try to have a mental picture of that. So I'll just show some videos to explain what I've been talking so far. So now for the across track scanner, um, that also known as whisk broom. So let's just see how it captures images of the earth. So this is what we have here. So just in a moment, it would show us why it got the name across track, which is the whisk broom. Right now, so this is how it is scanning. So if you notice, it is scanning this way, right? Like imagine you are sweeping, you go sweep this way, you come, you sweep this way, you sweep this way, you sweep this way. So I'll just play that part again. So see, it's taking, it's going this way, it's going this way, it's going this way, it's going this way, it's going this way. So that's why it's like it gets named whisk broom, like you're sweeping from one end of the room to the other end of the room. So look at that. So it goes this way. You are sweeping, you sweep, you sweep, you sweep, you sweep. So basically, that's why it got the name. So now let's look for now let's go to the next, which is push broom. So now we would understand what I was trying to talk about while I was trying to talk about the forward motion. I was trying to explain the forward motion earlier, which it got the name push broom, like pushing something forward. So now we would like see this video and we'll understand more. So now if you look at this motion, it is moving the way it's scanning the earth. It is in a forward motion. It is not, for the whisk broom was going side by side. But if you look at this, it is pushing forward. It is like taking it, it is taking everything once. It's like pushing forward like along that track. Look at that. It is moving forward. So it is moving forward this way. It is moving forward this way. Moving forward this way. So that is why it's called push broom. You're pushing the broom forward. You're like rolling the carpet or the rug. You're rolling it forward. But compared to the across track, which is going this way, the across track is going this way. But the push broom is moving this way. So basically, those are like the different type of scanning we have. So as well, I just felt it would be nice to talk about some satellites and their resolution. So we have different type of satellites. We have the Landsat, we have Spots. I'm familiar with Landsat, Spots, and Iconos, Sentinel, and some other type of satellite. So basically, these are like the launch dates of all the satellites, and also the spectral resolution. For the blue, for the so for Landsat, we have like different Landsats. We have Landsat, 7, 8, 9 was recently launched. So these are for the older Landsat mission. This is the 1999 probably Landsat. I think probably 4 or 5. I'm not so sure. So these are like the spectral bands, and these are like the spatial resolution. So you could just like check different satellites and their spectral bands and their spatial resolution. So that will be a wrap for this week course. So as usual, at the end of every video we give assignments. So the assignment for this week is to give a brief explanation about the following. So basically, the reason we give the assignments, we are trying to demystify remote sensing. We're trying to explain remote sensing. So we believe we believe we have to do some due diligence on our own part to basically understand more about what we are trying to like disseminate. So we just try to like we remove or not talk about some important some stuff that we deem important, and we just feel you should do it as assignments. So basically, we'll also drop a link to answer the assignment. So the assignment for this week is to just give a brief explanation on satellite orbit characteristics that we didn't talk about. So the inclination angle, ascending and descending paths. So just do this assignment. Then another assignment is to talk about imaging sensors and non-imaging sensors. So thank you so much for joining this week. We really do appreciate you and your time once again. If you've not subscribed to the channel, do well to give us a subscribe. Do well to subscribe to the channel. And we found this video helpful in any way, kindly give us a thumbs up. We appreciate you once again. You can follow us on our social platforms, on LinkedIn, on Twitter, on Instagram. and also kindly subscribe to our channel. And as I mentioned earlier, we are building a geospatial community. So if you want to join us on Slack, I would also drop the link in the description so you can join us on Slack as well. And now, week 4 is the final week where we'll be talking about some errors that these satellites encounter. So we'll also be talking about how these errors are corrected, and we'll wrap up with digital image processing. So thank you so much for your time. We appreciate you.